Hello, thank you for watching. Thank you for tuning in. We're doing lesson 5.3 for geometry. I want to start this off by saying if you have not watched the 5.1 video, I think you should watch like the first few minutes of it and watch me do one of those. We are doing the exact same thing as 5.1, except with specific types of triangles. So if you have watched 5.1, let me just briefly remind you that in 5.1 we were taking a seemingly random triangle, and it wasn't seemingly, I should say. It literally was just a random triangle, and we were rotating it 180 degrees, and we were saying, look, this is a parallelogram. Well, what if it wasn't a random triangle? What if it was a specific type of triangle? If we could rotate a specific type of triangle, could we create a more unique shape? Because in general, let me say it right now, rotating a triangle 180 degrees will always result in a parallelogram. But what if that triangle is a right triangle? What if that triangle is isosceles? What if that triangle is a right isosceles? What kind of shapes are we going to get? And that's exactly what we're going to look at. So the first triangle that we have here is a right triangle. Also, let me say I don't have my iPad today, so I'm using my mouse to do this today. So sorry. But if we rotate a right triangle, you can see it's a right triangle because of the right angle. Okay, so let's take a right triangle and rotate it. So I've already prepared a right triangle here on GeoGebra, right? So here's a right triangle, triangle XYZ. If I were to rotate it around the midpoint, and it's been labeled K there, 180 degrees. So rotate this triangle around this point 180 degrees. What shape would you say that I have there? I hope you're thinking a rectangle, and you're 100% correct, right? This is a rectangle. It's also a parallelogram, right? Rotating a triangle results in a parallelogram. Rotating a right triangle results in not just any old parallelogram, but specifically a rectangle, right? This 90 degrees right here got rotated around and became 90 degrees up here, right? Resulting in 90 degrees everywhere. Pretty awesome, right? So we now have a rectangle. And that would have happened no matter which way I rotated the shape, I'll have you know, right? If I rotated it around this midpoint, it's still a right triangle, right? Or wait, it might matter. Ooh, I might have just misspoken. It might matter. Let's see. What's it going to look like? Okay, that's definitely not a rectangle. I misspoke. It's not. I think it is specifically the hypotenuse. I think it's specifically the hypotenuse. Let's see. Let's do it across this one. We're investigating, right? We're investigating. We're learning together. Yeah, it's specifically the hypotenuse. I misspoke. It's not just any side. It's specifically the hypotenuse, the long side. So so if you rotate 180 degrees along the hypotenuse, then we get a rectangle. Okay? So let's get back to that rectangle, shall we? Rotate the triangle. K is the midpoint of the long side, right? Which is the hypotenuse, right? These two sides are the legs, and then that's the hypotenuse. And boom, we have a rectangle. So let's go back. So what type of triangle are we starting out with? This is a right triangle, okay? Does this rotation result in a parallelogram? Yes, it always will, right? Rotating 180 degrees always gives you a parallelogram, as you saw, right? I did the two other ones, and those were both parallelograms, but they didn't look like rectangles, right? It was specifically when we rotated along the midpoint there of the hypotenuse. So what did we end up forming? A rectangle. The answers to these, well, here, let me go back to my drawing, right? We saw that the answer to all of these, when I measured the angles, it all became 90, right? You saw that. 90, 90, 90. Okay. So the answer to this is, what angle is formed at R and S after we rotate? 90 degrees. And then it says, what is the length of RS and UT? What do you notice? So R to S is this diagonal, and then U to T would be the other diagonal. So if I came in here and drew the other diagonal, I mean, what do you think? Just looking at these two diagonals, what do you think? They look about the same, right? And you would be correct. The diagonals are congruent. If you recall from parallelograms, we knew that diagonals bisect one another, and that's still true. Okay, if I were to measure the distances here, right, this has been split in half. They're both 4.3, but they're all 4.3 for a rectangle. That's not true about any old parallelogram. It's only true for rectangles. So we're getting more nitty-gritty here, right? Parallelograms, think of it as a hierarchy. Parallelograms is this overarching thing, but we can get more and more specific. What if we make it a rectangle? What if we make it a square? What if we make it, right? We can get more and more specific, okay? So there is our rectangle. So again, rotating any triangle will result in a parallelogram. Rotating a right triangle will result in a rectangle. What are we looking at here in example 2? What type of triangle is this? The two legs are the same. The two legs are the same. That's what we called isosceles. Okay, that's what we called isosceles, when the legs are the same. So let's rotate around that third side. I've already prepared a isosceles triangle for us. So here, I'll measure it to show you that this distance is the same as this distance, okay? You see that? And now if we rotate around the third side, around point L, let's take a look at the shape that we get. I rotate 180 degrees. Okay, that looks a lot like our normal parallelograms that we've seen. But there's something specific here. We just created a parallelogram that has all four sides that are the same. That hasn't been true. Whoops. That hasn't been true before, right? We've always said opposite sides are congruent. We never said all four sides are congruent. But because the legs were the same distance, that should say 5.9. They should all be the same. I think GeoGebra is doing a weird rounding error. Oh, I think it's because M's not directly on that. I'm not sure why a letter didn't appear there in the first place. Can I just... right there. I think that's close. Not sure why a letter didn't appear there automatically. That's weird. There we go. 5.9 in. All right. Can you guys just pretend that says 5.9? It's supposed to. It's just doing a weird rounding thing. There we go. All right. Okay. So there is our shape. You might know what this is called. You might not. That is specifically called a rhombus. That is a rhombus. A rhombus is similar to a square, right? When you think square, you think all four sides the same, right? I think that's one of the main things that everyone thinks of. When they think of a square, they think all four sides are the same. Well, clearly, this is not a square, right? Yet all four sides are the same. What is the other detail that's true about squares? Well, they need right angles, right? This thing is tilted. So a rhombus is like trying to be a square, but it just didn't quite make it, right? A rectangle's trying to be a square too, because it has the right angles, but it's just longer, right? Or taller. So both of these shapes are trying to be squares, but yet they're just not quite there. So our rhombus here, all four sides are the same. So if we go back to our notes here, does this rotation result in a parallelogram? Yes, of course. Anytime you rotate 180 degrees, anytime, right? Anytime you rotate 180 degrees, you're always going to get a parallelogram. What is the measure of the angle formed by the intersection of the diagonals? So that question specifically is asking, okay, if we connect this diagonal to this one, and my point, I don't know why a point didn't automatically appear there. It's kind of annoying, but the measurement is supposed to be 90. The measurement is supposed to be 90. So let's see if it is 90. Beautiful. Okay, it did. It worked out for us. Okay, perfect. 90 degrees. Yep. So over here, you'll notice that the diagonals did not intersect at 90 degrees. Clearly, that's much bigger at 122.1. Over here, we got a nice clean 90. I encourage you to fiddle with GeoGebra if you ever want to. If you just Google search the words geometry GeoGebra, because GeoGebra has other things besides geometry stuff. So if you Google search geometry GeoGebra, it'll immediately pop up with this thing. Okay. And you can fiddle if you'd like. What happens to the angle of the quadrilateral when you draw in the diagonal? Remember, two equal sides of a triangle means you will have two equal angles as well. So what that's saying, okay, so don't get too intimidated by that. When you draw in a diagonal, right, which I drew in, right? I drew in this E to M line. What did we just create? We just created another isosceles triangle. You realize that? Right? Because let me kind of reinforce that by like drawing over it. Let me make this a little darker. Right? That's that dark triangle that I just drew. That's also isosceles. What makes a isosceles triangle? When the legs are the same. They're both 5.9. And when the legs are the same, the angles are the same. So this angle is the same as this angle. They're both 29.6 or 8, whatever. I can't read it very well. 29.8, right? Kind of cool, right? So this was an isosceles triangle rotated, and we end up kind of creating another isosceles triangle, right? And guess what? If this is 5.9 and this is 5.9, and then over here this is 5.9 and this is 5.9, well, then the same thing's happening over here, right? These should also be 29.8. I mean, it's an identical triangle. The rounding's being stupid. It's supposed to say 29.8. The rounding's being stupid, okay? It's the exact same triangle over here as well. See, that one's coming up 29.8. I don't know why that one rounded to 30. That's weird. My point still stands, right? So we have another isosceles triangle. So how could we think of this? The diagonal is bisecting the big angle, right? From F to E to D, right? That large angle is how big? 60. And if you were to split it in half, again, the weird rounding, I don't know why it's being dumb. If you were to split it in half, you would get 30, right? Which I guess this one showed up as 30. Not sure why the other one didn't, but you get the point, right? Hopefully you get the point, right? Everything's symmetrical. It's symmetrical. That's the best way to think about it. Like it's literally splicing it down the middle. It's fantastic, okay? So what happens to the angle? It is bisected. All right, so what if we took not just a right triangle and not just an isosceles triangle, but a right isosceles triangle? So it not only has a right angle, but also the legs are the same. I bet you could take a guess as to what shape is going to be created. If this made a rectangle with a right triangle, and this made a rhombus, what quality is so unique and nice about this? I'd like to think the 90-degree angles is pretty fancy, right? 90 degrees everywhere. And what property is so unique about this? Well, all the sides are the same, right? And what did I say earlier? These guys are trying to be squares, but they're not. This thing right here with a 90-degree angle and legs that are the same length. Stupid rounding error. Ignore it. The legs are the same length. So freaking stupid, right? I don't know what's happening there. Clearly, this tool is not the most incredible. And then we rotate it along the hypotenuse 180 degrees. You betcha we have created a beautiful square. We've created a beautiful square. How about that? So, when you rotate a right triangle, you have these qualities. Oops. You have these qualities. When you rotate an isosceles triangle, you have these qualities. Well, when you rotate a right isosceles, you're merging all of those characteristics, right? In this square, guess what? Our diagonals are congruent, just like the rectangle. Well, guess what? When you draw in a diagonal, you're bisecting the angles. Like over here, I'm just trying to move. Like over here in a rhombus, right? This became 30-30. Well, guess what? If this is a 90-degree angle and we're bisecting it, it became 45-45. Rounding error, ignore it, okay? I really wish it would be more accurate, but what can you do, okay? So 45-45. Look at that. So the qualities are merging. The diagonals were the same. The diagonals were the same. The diagonals bisected. The diagonals bisected. Guess what? What else was true about the diagonals? We had a right angle. Well, guess what? If rounding doesn't kill me here, we should have another right angle. Close enough. In a perfect world, this would work out. I'm sorry that it's not working out. I'm trying my best. All of the qualities from this rhombus and all of the qualities from this rectangle are combined together. So, what type of triangle are we starting with? A right isosceles. Does this rotation result in a parallelogram? Yes, of course. What type of parallelogram? A square. We end up with 90 degrees everywhere. Will it have the same properties as number 1? Yes. Will it have the same properties as number 2? Yes. Right? And there's lots of things that you already know about squares and rectangles, right? Please do not think just because you're older and we're in high school, there's something new that I have confidence that we all know qualities about rectangles and squares, right? It just kind of comes naturally, right? We've seen rectangles and squares all of our life, right? There's no surprises here, okay? There's no surprises. With that being said, since I don't have my iPad today, I don't think I want to try to draw on these with my mouse. I think let's just keep the video short. We did what we could with the computer, and I'll talk some in class. So I think let's keep it there. I encourage you to re-watch me rotate. I encourage you to rotate triangles on your own and see what characteristics you can spot, right? I encourage you to do that. And I will see you in class. Thank you for watching.